So, so now how would we train such a network? Well, one way to train such a network is, to define what is the loss, right? So, for regression problems, our loss is the usual squared loss, right? So, our regression problems loss will be, a neural network of x comma, let me call it theta, by which I mean when you pass the input x to a neural network whose weights are all parameterized by theta. When I say theta, it means in the previous example, this is W1 to Wk and W out. All of this put together I am calling as theta, all the parameters of the neural network. And now the entire neural network is fixed once I fix theta, and then I give x, right. So, now for this particular x, let us say xi, which is my first ith data point. Now, this is what the neural network would predict. Now, the loss would be this minus yi, right. So, comma yi in general. For regression problem, this can be neural network of xi parameterized by theta minus yi squared, and then I will sum it up over all data points as usual, right. So, now the way you have to think about this is, this is analogous to W transpose xi. If you just had a single, you only had one neuron in the hidden layer, then there is only one W, and this can be thought of as analogous to, and then there is the activation function is an identity function, then this is just W transpose xi. Somehow you are outputting something based on the input, and that is what is your predicted value, and this is the actual value, and then as usual you are looking at the squared difference. Now, of course, we need to find this theta. Now, if your activation function is a differentiable function, a continuous function and so on, then what you can do is you can start with some parameter initialization, and then you can do gradient descent with respect to theta, right. So, learn theta star using gradient descent as usual, right. So, because now your whole neural network is parameterized by theta, and theta is some high dimensional object. It includes W1 to Wk and W out. And now as you change each entry of W's, then that will affect my output in a certain way, and that change is captured using the gradient, and so I can take a step in the negative gradient direction and so on. So, now as the number of parameters that we have in our neural network increases, this theta is going to become a very high dimensional object. Why would number of parameters in our neural network increase? Well, here we had a very simplified neural network where we had one hidden layer, but now we can think of a case where we have multiple hidden layers, right. So, for instance, all of these guys are voting based on my input data points somehow, and now you are kind of combining these votes to create more votes, right. So, this is layer 1, this is layer 2 and so on and so forth, right. So, each successive layer is kind of trying to operate at one level above the previous layer, right. So, it is combining the votes of the previous layer, so, and it is voting on the combination and so on and so forth. And you can add multiple layers here, right. So, let us say I add L such layers, and now finally I will combine using an output layer, right. So, this is output layer to produce my output. This is of course the input layer. Now, for this neural network, you have many more parameters, right. So, every neuron corresponds to one W that we need to learn, right. So, the W's might be in different dimensions based on which layer this neuron is in. So, for instance, if it is in the first layer, then the W will depend on the input layer's dimension. So, these would be in d-dimensional vectors. The second layer will depend on how many nodes that we had in the previous layer, and that is a design choice, right. So, we can try out different nodes. Typically, all the layers from 2 all the layers from 1 to L will have the same number of nodes, but that's not a strict necessity. You can try out with different things, but then depending on that, the parameters that you have to learn can blow up, right? So it can become a very large number. So now then question is, how easy is it to compute the gradient of this complicated looking network, right? So for a given theta. Well, it is a bit complicated, but then there is an efficient way to compute this gradient, right? So, and that just uses, you know, the chain rule of differentiation, right? So, the gradient computed taking advantage of chain rule. Again, we won't do this in detail again, because this would be dealt with in deep learning course, but all I am trying to say is that this gradient with respect to some, if you give me some parameter values W1 till Wk, I mean all the parameter values, if you give me theta, then I can compute the gradient of this neural network at theta efficiently by taking advantage of the chain rule of differentiation, and the algorithm that does this is actually called as the backpropagation algorithm. Right. So, it is simply an algorithm that is trying to compute the gradient of this neural network, of a specified neural network at a given value of theta. Now, once you can compute the gradient, then you will update your W's based on taking a negative step in this gradient as usual. It's the standard gradient descent. But now, the interesting thing is that because the output is not a convex function of these parameters, the gradient descent is not going to converge to the theta opt, right. So, that value of the parameters which will minimize our training error, right. So, the loss function, right. So, it need not converge to you know, the optimal, the global optimal of this function, because this is a non-convex function, right. So, it's going, especially this is a very high dimensional function because there are too many parameters and this is a very highly non-convex function. So, you will converge to a local minima, right. So, gradient descent converges to local minima. And now, if you take again a deep learning course, you will understand, you know, when how to, you know, deal with this problem, right. So, typically I mean, first glance it appears that okay, so we wanted to find the global minima, which was easy in the case when the loss function was a convex function of the parameters. Here the loss function is not a convex function of the parameters, so we might end up with not necessarily a global minima, we will only end up with local minima. So, it appears that this method may give us poor solutions. So, now how to deal with this and how it typically works very well in practice, if you initialize your algorithm carefully and if you do some, you know, clever tricks to gradient descent to make it slightly different. You just don't follow the direction of the gradient, but you do slight tricks with respect to the gradients would be covered as part of a deep learning course, right. So, so basically the ideas are similar, right. So, you set up a loss function, the loss function has some parameters, but then the function is not a convex function of the parameters of interest. So, your gradient descent may not converge to a local minima, still you can, you know, it converges to something that is very reasonable in practice. And the reason why that happens and how you can, you know, do these tricks and so on to get it working it would be part of a deep learning course. But in the standard classical artificial neural networks method, I mean, your backpropagation is a technique which simply computes the gradient. Now, this backpropagation is common for both regression and classification, right. So, right now we have spoken about regression where we put down this loss function as the squared loss, but it need not be the squared loss. If you are working with a classification problem, so let us say you have a classification problem, then what would happen is that again you will have some input layers and some hidden layers. Let us say we have input layers x1 to xd and you have all these hidden layers and then you kind of what you do is, you can have multiple layers. This is layer 1, layer 2 and so on and so forth. If it is a binary classification problem, then you have one output layer which will produce, let us say, sigmoid of W out transpose, whatever is the input, right. So, input to this, right. So, which is just, this is what I mean by input. Whatever this takes as input, it will have a W corresponding to each weight corresponding to each of these edges, and then it will do W out transpose input, and it will do a sigmoid, which means that basically we are predicting probability of y given x, right. So, this is a sigmoid function as usual. So, now there is an actual y sitting here, and now you can define an appropriate loss which depends on how well this probability of y given x matches the actual y, right. So, this is let us say 0.1 then your loss will be less if y is 0, and if it is 0.9, which means that you are more likely to say that y is 1, but then the actual y is 0, then the loss will be more, right. So, basically you can use what is called as a cross entropy loss, which kind of measures how close are these two things with respect to each other, right. So, now the remaining thing is exactly the same, right. So, because your neural network is still is a function of all these parameters theta, and the only thing that is going to change is in the final layer, where instead of outputting a real number, you are now going to do a sigmoid of a real number and predict the probabilities, and then now you have to compare the probabilities with the with the actual output y. And using the cross entropy loss, and then again you will do the gradient with respect to this new loss function. Everything else is the same, right. So, because we need to compute the gradient, you want to do a gradient descent, you want to compute the gradient of this loss function with respect to the underlying parameters. You do the same thing, you do a back propagation based algorithm, which again takes advantage of the chain rule of differentiation because the chain rule is an intuitive thing here, why it should why it should be used here, because you have multiple layers, and then what does the gradient essentially tell you? The gradient is telling you that if I change one weight, how does it affect the output, right. So, now this one weight will affect the weights on the next layer will affect the weights of the next layer, and so on and so forth, and so it has to affect the output, right. So, now because there is this layer wise structure in our neural network, we can use this structure to do this back propagation more efficiently, right. So, and that is where you kind of gain in doing back propagation by taking advantage of the chain rule. It is an efficient way to compute the gradients, right. So, once that is done, everything else is basically the same, right. So, so basically the conclusion then is with respect to neural network is that neural networks learns local minima of non-concave functions. Typically works very well in practice. Now, I will add that when I say practice, especially for unstructured data like images or or text or even speech and things like that, where you're not given a tabular column of features, but then you are just given some unstructured pieces of information from which you need to learn these features, so to say. Of course, depending on whether it is text or whether it is time series data or whether it is speech or whether it is images, now your neural network architectures have to be different for each of these different modalities. Now, again, when you take a deep learning course, you will understand that how today's state of the art neural networks kind of use some information that we know about these modalities as part of the architecture, so that it kind of learns, you know, these feature mappings very well. So why do I say this as feature mappings? So one way to think about this is as follows, right? So you can think of what the neural network is doing for even for a regression problem. It's taking as input and then it's producing an output, right? So it's producing some real value here. Now you can think of the neural network itself as if it is mapping the input to a real number. That's one way to think of it. The other way to think of it would be to think of the neural network as doing two different things. In the first level, you can think of, you know, what it does till the last layer, and then you can think of what it does in the last layer. Now, one way to interpret the neural network's workings is by saying that the neural network learns some feature mapping from layer 1 till layer L. So basically this input data, which is an RD, let's say, is mapped to some RM, which is, you know, you have 1 to M nodes in the last layer. So this is the last layer, layer L has M nodes. So you are mapping RD to RM using some nonlinear map, which is what this layer 1 to layer L is doing. And now after you have learned this map, what the output layer is doing is just doing a linear function on the last layer, right? So on the learned map. So you learn a nonlinear map and then you do a linear function in the nonlinear space, right? So which should be reminiscent of what kernel machines typically do, right? So it is like implicitly you're trying to map your data to a higher dimension, and then you are doing a linear function. You're learning a linear function in this high dimension. There in the kernel machines, so you specify the kernel, which means to say that you specify the mapping from low dimension to high dimension. Let's say if it's a polynomial kernel, we are saying that you take the original features and then, you know, you take height and weight as features, you do height squared, you do weight squared, height into weight, and so on and so forth. Whereas here, you know, neural network can be thought of as doing both feature learning and weight learning together. Because you're not really saying what are the features to use in the high dimension. That is also being learned in this particular neural network, right? So the first L layers learn this feature mapping together with the weights that should be learned after you do the mapping to the high dimension, which is what the output layer is doing, right? So it's jointly learning both features and the parameters in some sense. That's one way to think of it. Now, the moment you think of it like this, now for images, certain type of feature mappings might be more intuitive. For text, certain other type of feature mapping might be more intuitive, and so on and so forth. So now you can design your neural networks, play around with the design of your neural networks to suit the modality itself, right? So if it is images, perhaps, you know, looking at edges, looking at some properties, some specific things, right? So looking for edges, corners, and so on and so forth, looking for simple shapes might be relevant things that the neural network should do. Now you can, you know, set up the neural network such that it kind of starts looking for these things in some sense, right? So the way to design these things will be, you know, will be part of a deep learning course where you will understand how to come up with neural networks which do good feature mappings and also learns the mapped feature to the output. That is always going to be straightforward. A last layer is always going to be a linear layer, typically with a if it's a classification with a sigmoid and so on and so forth. But what kind of architecture should the neural network have so that you kind of do this mapping for this unstructured data very well will be part of a deep learning course. We won't talk about that much here, but then if you take a deep learning course, you will see that you know, for unstructured data, some variants of these neural networks called convolutional neural networks, which are very, very popular, especially for image-based data, because convolution is a very useful image-based operations. For time series-based data, you will have something called as recurrent neural networks, which works well for time series-based data. There are something called as LSTMs, which are again long short time memory based neural networks, There are something called as transformers and attention models and so on and so forth. These are all examples of how you can develop in some sense nice neural network architectures, which are essentially nice way to map our input data to some useful feature space, so that our problem of classification or regression becomes easier, right. So again, these will all be covered as part of a deep learning course. I'm not going to do that in this course. To summarize, summarize whatever we have seen so far in neural networks is that it is basically at the end of the day, it's just a nonlinear map from input to output, but then it's just not arbitrary nonlinear map. You kind of specify this nonlinear map using an architecture, and the simplest architecture that we have seen is this one layer architecture, but then there could be multiple layers, and all sorts of architectures which map input to output. And once you have specified the architecture, the way to learn this, the parameters of this architecture would be to do something called as backpropagation, which is nothing but gradient descent, an algorithm to compute the gradient, and then you do a gradient descent. You will typically end up with a local minima of the loss function, but that usually is very good in practice. In practice, these are very powerful algorithms. They beat state-of-the-art classical machine learning algorithms that we have seen a lot in this course, specifically for unstructured data. For structured data, still I wouldn't say these are the best possible algorithms. We might have something like a boosting or a support vector machines are still very good algorithms when you have structured data. When you have unstructured data, because the modern day neural networks build these feature maps very carefully, they outperform classical methods like support vector machines or logistic regression, where the kernels are not necessarily tuned to a particular modality, right. So the neural networks are very competitive in today's, they give you state-of-the-art performance for most unstructured data based problems, whereas for structured data, we will still use several algorithms learned in this course, right, from support vector machines to logistic regressions.